Hi guys, welcome back to my system design series. In today's lecture, we are going to discuss about two important concepts of distributed database. Those are multi-leader replication and leaderless replication. If you haven't watched the previous video, then kindly make sure you watch it so that you will understand what do you mean by replication, what do you mean by replication lag, what do you mean by single leader replication, and what do you mean by multi-leader replication. Okay, let's do a quick revision. What do you mean by multi-leader replication? It allows more than one node to accept write operations. Instead of single primary, you can have multiple leaders, also called masters, in different locations. Each leader can take the writes from the clients and then share those writes with the other leaders. So, every leader is also the follower of other leaders. They all replicate each other's changes. This is also called master-master or active-active replication. When you have several leader nodes, you need a replication topology, a way to arrange connections so that each leader's writes get propagated to others. With two leaders, it is very simple. They just sync with each other. With more than two, there are few common topologies. They are circular, star, mesh, that is all to all. Each of them has pros and cons. Let's break it down. In circular topology, in a ring, each node sends a writes to its neighbor in a circle, which forms a loop. For example, A forwards to B, B to C, C to D, and D back to A, circulating updates around. To prevent an update from looping forever, each write is tagged with an identifier. So, a leader can ignore the update which it has seen before. This stops infinite loop. So, pros of using ring topologies are it is very simple and uses predictable path. Because of that, it needs a lower bandwidth usage since each update travels a fixed route. Cons of using this topology are it is a single point of failure. If one node in the loop goes down, it breaks the chain and replication can halt. Also, an update has to traverse several nodes to reach the corner of the rings, which means the higher latency for the replication. MySQL's default multi-master setup is often a circular replication, which is straightforward but inherits this kind of limitations. Now, let's discuss the another one, that is a star topology. In star, one central node acts as a hub. All other nodes send their writes to the hub and the hub forwards all the writes to all other nodes. It is like broadcasting center. The same loop prevention, that is a ID, is needed to avoid infinite loop. So, the pros of using star topology is centralizing communication can simplify monitoring and maybe conflict resolution. Cons is the hub is acting as a bottleneck and single point of failure. If the central node breaks, the spokes can no longer exchange updates. Also, the hub might get overloaded if there are many writes. This is a key to a traditional publisher-subscriber model. Oracle's older multi-master replication and some SQL Server setups uses a hub to collect and distribute changes. It is easier to reason about, but it is better if you keep the hub healthy. The star topology is like a central post office. All neighborhood mail goes through it. If that post office closes, mail can't be circulated between neighborhoods. Another one is mesh topology or all to all. Here, every leader sends their writes to all the leaders directly. If there are 5 leader nodes, each one has the connection to other 4, which forms a dense web. Pros of using this is it provides a high availability. There is no single point of failure because if one node goes down, all the other nodes can communicate with each other directly. Updates propagate quickly, which causes the low latency since they go straight to every node without intermediaries. The load of writes can be well distributed. Cons of using all-to-all topology is it introduces lots of communication overhead. Many connections to manage, potentially more network traffic overall. Also, conflict resolution becomes more complex because writes can arrive in different order on different nodes. With every node talking to each other, keeping a consistent global order of track is tricky. For an example, consider a scenario. User creates a document on leader 1 and almost simultaneously other user updates the document on leader 2. If leader 2's update reaches to leader 3 directly faster than leader 1's update, leader 3 might see an update for a document that it doesn't know it exists yet. We will see how to handle this kind of conflicts in the upcoming lectures. Real-world system that uses mesh includes CouchDB, which lets each replicas to sync with each other in the cluster, and some multi-region MongoDB or new SQL configurations. Mesh gives resilience but needs a careful engineering to handle all the concurrent updates. The all-to-all mesh is a kind of a group chat where everyone can send the message to everyone directly. It is great because no single person is in charge of relaying the message. But the messages might arrive out of the order or at slightly different time on each other's phone. Have you ever saw a group chat where you are able to see the replies before the question has been asked? That is because of the network lag. And that is a kind of ordering issue which we need to handle when we are using all-to-all mesh. No matter the topology, the key is that every write will eventually reach to every leader one way or another. In circular or star topology, this may involve write forwarding, passing along the update through intermediary node until all have it. But how about the fault tolerance? Multi-leader replication can help with the fault tolerance. If one leader goes down, the other leader still accepts the writes. But the topology affects how well it tolerates the fault. In a ring, as we noted, one break node can fail the chain of communication unless you have some mechanism to route around it. Without that, the ring might stall until the node is fixed. In a star, if the peripheral node fails, it's okay. It just won't receive the updates until it is back. And the hub can buffer or later catch it up. But if the hub fails, the replication will be stopped for everyone. So, the hub is the critical point to protect. In all-to-all, the system is most resilient. If one node fails, all the other nodes are still connected and can continue sharing the updates with each other. No single failure will isolate the rest. The failed node, when it comes back, it can retrieve the updates from the other nodes. To sum up, there are different ways to wire up multiple leaders, each with trade-offs. A ring is simple but brittle. A star is simple and easier to manage but has a vulnerable heart. And a full mesh is robust but complex. Okay, let's talk about the conflicting writes and ordering issues. What happens if those parallel writes get out of sync? Let's find out. Now, let's discuss the problem of conflicting writes. This is the big challenge. What happens if the two leaders get the conflicting writes at the same time? Because in multi-replication system, clients are writing to multiple leaders. For example, leader A, leader B, both simultaneously. And there is no single traffic cop who is going to sequence this all the writes. So, because of that, conflicts will happen. For example, when you are working in a Google Doc or maybe Google Sheets, there are two users. So, for example, both of them are working or updating single cell and making it, suppose user A is making it 1, 2, 3 and user 2 is making it 4, 5, 6, both at the same time. After the update, user A will get the update of user B and user B will get the update of user A. But now, both of the user are not able to see their own writes, so they will think that what happened, they have just written and how it has been deleted or how it is not there. That is called the writes conflict. Another example, as we discussed before, we take as a WhatsApp group. There are three members. Leader A, leader B and leader 3 are kind of a user A, user B, user C. Suppose user A have asked a question that are you guys going to attend a meeting tomorrow? And after that question, user B or member B have replied yes. But member C is getting the answer yes before the question. So this whole situation is violating the causality order of events. This conflict and out of order scenarios are the pain point of multi-replication system. Unlike single leader which can simply reject a second concurrent write, or serialize them, multi-leader has no inbuilt arbiter. So, we need the strategies to resolve these conflicts once they are detected. Okay. Let's now discuss how to resolve conflicts in multi-leader replication systems. Handling conflicts is crucial. There are few common approaches via which we can resolve the updates in multi-leader replication. So one of them is last write wins. This is simple and automated rule. Whichever write is the latest one, it will override the previous one. So how do we decide the latest writes? So for that, each writes have the timestamp. Often the originating the leader's timestamp or a logical timestamp. When the conflict is found, the newest version of the timestamp is kept and other is discarded. This can be also called the highest ID wins if we are using the monotonically increasing counter. The pros of using this is it is very easy to implement and ensures the convergence to the single value quickly. Many systems like Cassandra are using the last write wins by default. They simply attach the timestamp to the each write and simply pick the largest timestamp for the true update. Cons of using last write wins is data loss. If two people truly made the different changes, one of them changes is getting lost. Also, relying on the clocks is dangerous. What if one server's clock is wrong? For example, if it is few minutes fast, its update might always win, even if they weren't truly later. So, last write win is only accepted for the data where losing one update is okay, or when we can ensure the synchronized clocks. Second is custom merge or application level resolution. Instead of automatically dropping one update, we can program the application to merge the changes in a meaningful way. This write means recording both the values and resolving later. For example, two users are working on the same files and after committing their changes, the second user gets the conflicts. So he have to resolve the conflicts and then only he can merge his own changes. This means that the Git is storing both of the user's changes and it lets the user decide which changes he or she wants to keep. Similarly, Dynamo style database also stores the different versions and it lets the user decide that which version he or she wants to keep. The pros of using this is no data is blindly lost. You have a chance to preserve whatever is important or crucial for you. Cons of using this is it is very complex. The logic is specific to your data. That is, you have to write and test the merge logic. It is essentially more work for the developers as well as for the users. Tools like CouchDB takes this approach. When conflicts happens, CouchDB stores both the versions and you have to decide which version you want to keep in the application. The next one is CRDTs. That is conflict-free replicated data types. A CRDT is a special type of data structure which is designed. They can merge mathematically without conflict. The idea is the operation on the data type are commutative. Order doesn't matter. Everyone will converge the same result when all operations are applied. Every increment is just +1. So, for example, two leaders are incrementing the counter. No matter what is the order or when they are merging, the final count is sum of both the increments. So, no conflicts, just add them. Likewise, there are set of CRDTs to merge the sets. You won't double add the same element, etc. And even more complex structures for text editing so that the concurrent insertions end up in a sensible order. CRDTs are usually used in the collaborative applications such as Google Docs, Figma, or Redis replication caches to automatically resolve the concurrent edits. Pros of using this is CRDTs allow merging without losers. No updates are lost and no manual resolution is needed. Cons of using this is they can only work for certain data types and insertions. CRDT design can get tricky, although many libraries now provides the common CRDT implementations. CRDTs are like kind of a magical whiteboard. For example, when two users are writing on the Google Doc, both of the changes are being able to seen in the Google Doc. So, both of the user's rights are in the final document in a sensible way. It feels like no conflict at all in the user's perspective. In practice, many multiple replication systems are using the combination of all of these strategies. For example, they might use last write wins as a default, but for certain fields, they are using the custom merge. The key takeaway from this whole discussion is conflict resolution is a must-plan aspect of a multi-leader replication. If you ignore it, eventually you will end up having the inconsistent data across all the leaders. Okay, next is leaderless replication. Imagine, suppose you are working in a group project and there are no leaders. No managers, no bosses. You have to do your own work without any instructions. Everyone do their own part of work and somehow it works. It is like a group project of distributed databases. Usually in the databases there is a one leader who manages all the rights and tell the another replicas like what they need to do. But in leaderless replication, they don't believe in managers. They just do their own work without just thinking about others. Every node can accept the right. Yes, every node can accept the rights. It is decentralized, free for all, and yet it works most of the time. Instead of sending the rights to the single node or single leader, the client is sending the rights to the multiple nodes at the same time. It is like a mass email. Everyone gets it. This leaderless replication approach becomes famous because of the Amazon's DynamoDB. The goal is to accept all the rights even if half of the replicas are down or not working. Usually in leader-based systems, if the leader is down, you can't write it. So, in leaderless replication, as there is no leader, your rights are being accepted by the replicas which are available. Whosoever is online, they are accepting your rights. It is more fault tolerance compared to the leader-based replication because it doesn't rely on one server. You are just YOLOing your data across the network. Suppose you have sent your rights to the multiple nodes, but how many of them have to say to you that they have received the rights so that you can say that your right is successful? So that's where quorum comes into the picture. Quorum is a rule that is to make sure that enough number of nodes agree in a distributed systems before something is considered valid. Quorum is just like a system saying that I don't need everyone to agree, just enough people so I can pretend that it is organized. For example, just imagine there are n nodes and here you can consider n equals to 3. There are 3 nodes and then you chose 2 as your right quorum. That means 2 of the nodes have to say that they have received the rights. And for the read quorum, we are taking as a 2. So at least 2 nodes must respond. So if read quorum plus write quorum is greater than number of nodes, that means you are reading probably the fresh data. So here R is the read quorum, W is the write quorum and N is the number of nodes. So 2 plus 2 equals to 4 and 4 is greater than 3. This means that your writes are overlapping with your reads. So because of that, you are probably reading the fresh data. And that overlapping node is a gossip queen and it means that it have the fresh data. But what if you take as 1 as your write quorum and 1 as your read quorum? So 1 plus 1 equals to 2 and 2 is less than 3. So now there is no guarantee that you are reading the fresh or latest data. You are now in the eventual consistency land where the data will be consistent eventually. Or maybe. So you should always choose the W and R as the bigger numbers. So the pros of choosing the higher numbers for reads and writes are you will get the high consistency. The system might be slower or less available, but here you are focusing on the consistency. But if you will choose the lower number for reads and writes, then you will have the high availability. It would be the faster but risky and have the stale data. So you have to decide based on what you want, consistency or availability. Okay. Now just imagine you are using the leaderless replication. What happens if all other replicas are not up to date? And that is where self-healing magic of read repair and anti-entropy comes into the picture. Okay, imagine that you have requested to read your bank balance. If it hits one of the replica, it shows that there are 500 rupees inside it. But if it hits the another replica, it shows there are only 450 rupees inside your bank. The client might get confused like what it is showing. But it turns out that replica 2 or server 2 have missed the latest update. And that is where read repair comes into the picture. Read repair is like a nosy friend who wants every single friend of them to be at the one place. If it notices that one of his friend is behind, it immediately drags that friend which is behind and it tells them to speed up and it brings to the latest update. This read repair will tell that the behind friend that why are you living in version 4? We all are on version 5. You have to catch up. So while you just wanted to know your bank balance, the system sneakily fixed that broken replica in the background. Read repair is like fix it when someone notices it. It is like cleaning your house when you know that your guests are going to be arrived in some time. But what happens if your request didn't hit that replica? Will it have the stale data forever? It is like that friend who is never got invited in any of the function. But that is where anti-entropy comes into the picture. It is the background janitor of the database world. Anti-entropy is like kind of a grandparents who are inviting us like every weekend or maybe on Sunday to check on that are we eating properly? Are you updated? Did you get the latest data or latest update? Anti-entropy just runs in the background, comparing the nodes, syncing missing pieces silently. Like a polite librarian, they use Markle tree to avoid comparing with every single record. It is smart gossiping. It says like, here is what I have got. Do you have the same? No? Then let me patch you up. Let's understand this by taking an example. Suppose you have created a playlist and you have added the songs. And out of 5 friends, 3 of your friends have received that song. Later, one of your friend checks the playlist and he found that this song was missing and he got that song, and this is called the read repair term. And once a week, all the 5 friends suppose meet in a cafe, and after that, all 5 friends compare the songs and sync them if they are missing out any of the song, and that is anti-entropy. So even if there is no leader, then also the playlist is being consistent, eventual consistent. This is not just theory. This leaderless approach has been used by many big systems. For example, Amazon uses the Amazon DynamoDB in shopping carts. Facebook uses the Cassandra to handle the data across the globe. They all use quorum based reads and writes, read repair and anti-entropy, so that the system stays solid without having a leader. So, in short, leaderless replication is like everyone is writer and no one is leader. And then read repair is like fix it when someone is watching. Anti-entropy is like fix the stuff when no one is watching. In result, you will get eventual consistency, high availability, and no single point of failure. So that's it for today's video. If you understood this concept, then make sure you like this video, and if you have any doubt, then kindly make sure you comment your doubts. And don't miss to press the subscribe button. It will help me and motivate me to make more videos. Thank you so much for watching.